Hello everyone, in this video we'll talk about independence. So two events E and F are independent if the probability of intersection of these two events is equal to the product of the probability of these two events. So if we have events E and F, the probability of E intersection F is equals the probability of E times the probability of F. In this case, E and F are independent. If two events E and F are independent, then the P of F given E is equals to the probability of F. So of course, if the probability of E is positive, is greater than 0. So in this case, the probability of F given E will be equals to a probability of F intersection E divided by the probability of E. But F and E are independent, so from this definition, their intersection will be PF PE times PF. So divided by PE. So the probability of E will cancel and we'll get the P of F. Also, if E and F are independent, so E and F complementary, the complement of F will be also independent. So the E and F complementary are also independent. If we have two events A and B and they are disjoint, so they are always dependent. If we have two events A and B and they are disjoint, that means there are no intersection between them, between events A and events B. There are no intersection between them, so their probability will be equal to 0. And in this case, will not be the product of this probability. So that means this formula will not be satisfied if the two events are disjoint. And in this case, we say they are dependent. The conditional independence. Two events A and B are independent conditional on event C if the probability of A intersection B given C is equal to the product of the probability of A given C times the probability of B given C. So in this case, we say that A and B are independent conditional on event C. And from this formula, we have the probability of A given B intersection C is equal to probability of A given C. We get it by writing probability of A given B intersection C, which is equals to, by the conditional probability definition, equals to probability of A intersection B intersection C divided by the probability of B intersection C. And also by the conditional probability definition, we can write this in another way. So it will be a probability of, we'll take this term and this term. So we'll have the probability of A intersection B given C times the probability of C. And also in the same way, we will use the conditional probability definition. We will get the probability of B given C times the probability of C. So the probability of C will cancel it, and we will have the probability of A intersection B given C. So it is, here we have probability of A given C times the probability of B given C. So we'll write it. We'll have A given C times the probability of B given C divided by the probability of B given C, and this will be cancelled, and we will finally get the probability of A given C. Here we define the pairwise independence. So we say that two or three events A, B, and C are pairwise independent if the probability of intersection of two of these events is equal to the product of the probability of each event. So for example, here we have probability of A intersection B equals probability of A times probability of B, and the same here for A and C and for B and C. But the probability of the intersection of these three events is not the product of the probability of this event. So in this case, we say that these events are just pairwise independent, but they are not independent. For example, if we have an event C here and an event A here and an event B here, so these three events are independent each one of other, but they are dependent. All of the events are dependent, so the intersection here is empty. The intersection A, intersection B, intersection C is equals phi, so they are disjoint. We define the independent trials if each sub-experiment has the same set of possible outcomes. So for example, if we have many experiments and each sub-experiment has the same set of possible outcomes, in this case we say that the sub-experiments are independent trials. So for example, the outcome of n tosses of a coin are the same in each case. For example, if we toss a coin n times, so in each time we will get the same result, the same outcomes, heads or tails. So in this case, we say there are we have some independent trials. For example, the probability of getting k heads after n tosses, if the bias probability is p, is the probability of getting k heads in n tosses sequences is n chosen k. Probability of this is probability of getting heads, is probability of getting heads, it is p as given here. So times the k, the number of heads in these sequences, times 1 minus p, which is the probability of getting tails, power n minus k.